next guest. It is Jan Marteen. Nope, that's Stefan. Now it's Jan Marteen. Hello, Jan. How you doing?
Jean Martin, right here. I'm good. I'm good. It's so good to see you.
It's so good to see you.
Actually, I've been seeing you the last 6 hours or so, but never gets old.
It's true. We're halfway through 6 hours in.
Hell yeah, high
Yeah,
five.
yeah. You're at the halfway mark.
We're feeling great.
You're
Yeah,
a
yeah,
halfway
yeah.
mark celebratory participant.
So, yeah, you look you look like you're going strong.
Oh yeah.
Yeah, it's going good. It's going good. We're having fun.
Mhm.
We've got lots to go still, but first we got to hear all about what you're up to, Jan.
Sure, sure. I didn't prepare any slides.
That's okay.
That's okay. You don't have to have slides.
Yeah, whatever you want.
In a bit in my workshop where I am, and I would like to start about talking about dust a little bit. I really like dust, kind of like this everywhere thing. But there's so many cool stories in dust. It's kind of like you get sand in dust from another continent on your car or what have you. There's also micro meteorites in dust, like your next roof probably has a couple of those in it. So the dust has lots of interesting stories, and one of the stories that captures me most is that there's actually a lot of DNA in dust as well. Like everything that's alive sheds a little bit, and these particles contain DNA often. And you can capture that, analyze it, and then you have a good sense of biodiversity, for instance, in your environment. Or you can learn about protected species, endangered species, maybe invasive species, health related issues. DNA in the airborne environmental DNA contains a lot of interesting and relevant information. But you can capture it, or the way it is captured, because there has not been an interest in it. It's fairly recently that people got interested in that specific type of eDNA, and people use like big devices that need to be powered by big batteries or directly from the net to function. So they're unwieldy, bulky. You cannot take them out in the field. So I designed and built a device to passively sample eDNA, and that's what I wanted to show first. I've got it right here. Um, it's a core. In the core goes a filter, whatever kind of filter you like. Then the core goes into the turbine. You close this thing. Underneath is a hole, so there's an exit for the air. The air powers the device. So the wind spins the device takes energy out of the air, and the particles settle in the filter in the core. The wind gets drafted through the exit below, and then you basically can wash out your filter and do your meta barcoding analysis or any other which way you want to look at eDNA. Uh, Turns out it works pretty well. I've done some research in collaboration with the biology department at the University of Leiden. We looked at Blight Oaks Zoo, and we hung this sampler and a couple of standard active samplers to compare them. And my design actually outperformed the battery-powered ones, so that was pretty cool. I open source it, thinking that this is something that everybody can print easily and put it on a GitHub, and then also suggested that if it turns out people actually mostly don't want to print them themselves, and they contact me to print them for them, which I'm happy to do. Uh, and that's starting out to be a little bit of a business. So I actually have to the right, I will show you in a bit, like 5 3D printers to actually be able to keep up with the demand of the thing, which is not something I expected to have to. I'm not an entrepreneur by inclination, but happy to roll with it. Now it turns out to be that way. So that worked out pretty well. But then, uh, as I started iterating on the design and build, this is like the fourth version or so. I actually needed to test these things, not just in simulation, which I do in FreeCAD, but also physically. So what I did is, and now I'm going to see if I can take the camera and the laptop with me to move around in our studio a little bit. There we go. Yeah, there you have it. So the next build was a wind tunnel over here, which pushes air to like about 10 meters per second, so that it's decent enough for the kind of things I want to test. It's not hyper speed hurricane, but like a stiff breeze. That's what comes out of this. And that was very fun to do as well. I took a motor from a vacuum cleaner. I designed the rotor, which is always a kind of technology I really like. Most technology kind of looks like boxes or like cylinders. These like rotors, they're like the most organic part of any kind of machine. So they're fun to think about and fun to design and make them work. Uh, but that was that was kind of sort of only the first traditional design I turned it out to need. Turns out I would benefit from a weather station as well. Didn't design it myself, the weather station. On top, it's like an eco-wid system, which is not open source or anything, but as vendors go, it's one that makes it easiest to share data and not try to lock you in into their ecosystem. And there's a smart citizen dust collecting, dust appreciation or UV light sensor as well. That's fully open source, paid from a European public funding. And of course, there's some of my samplers on it as well, so that I have a way to actually test my own samplers in the wild. If I have different design iterations, I will want to test them, and this way I can actually do that. Now that we're on the move, here's a couple of 3D printers around here, and then to the right, in the edge right here, I do my silicone casting, not necessarily relevant for this particular project. It's one of the things I have around in my workshop. Moving back to my desk. There we go. Now, after collecting, I figured I needed to transport samples as well. This is something I've been trialing at the Dynacon in Bali, which was such an amazing time. So most biologists feel feel only secure if they can put their samples in a freezer. But I figured maybe you can pack your samples actually in clay. It's like archaeologists, paleontologists, they find that clay contains DNA that's like sometimes even millions of years old. It makes sense, right? Clay kind of like shelters your sample from UV, from water as well, and it deactivates maybe also the enzymes that would attack your DNA. So I'm now in the process of working my way through the whole chain up to the analysis of the material. So not just capturing it, but transporting it as well. And the most recent recent bit that I've been designing is like a way to uh, filter particles to size. This is like a little basket with rings. It has agar in it. Uh, Later, I will add like an electrode to the bottom, to the floor. Then like this part goes on top, and then I can. This is actually the first time I'm trialing it. I just finished this last weekend, so I haven't had to try to experiment with it. And I'm going to put it in a plate because this potentially could be messy. There we go. If you have electrodes on the top and the floor of this, and you very in a very controlled way with maybe a stepper motor or so, push a sample containing liquid out over uh, the thing, you could in theory draw the particles to size because heavier particles will fall first and smaller particles to the outer rim, and then push them through the agar uh, in a like a yeah a gel electrophoresis kind of way almost. I actually think I have a better design than this one because basically it seems I'm reinventing gel electrophoresis, which why would you if it's already there? Um, yeah, so that's some. Oh, here's another thing as well. The people in Leiden actually wanted me to add a counter to the turbine so that so we have an idea how much air has passed through the device, which is in itself easy enough with like a Hall sensor and like a little board to do the math on the number of rotations and such. But I was like, I don't want a battery. The whole point of this was have like a no battery kind of prototype. So I actually designed this, where the turbine drives a motor in reverse, which generates electricity, which is then goes through like a diode and is captured by the capacitors. So at the end of your sampling period, you can basically measure how much charge you have in your capacitors, and then you also have like an idea of a proxy for how many rotations the device made over time. This probably is going to take a lot of testing before it works, if at all, because if a turbine moves very slowly, will it generate the same amount of energy compared to when it's turning very fast? Probably, but maybe not. In theory, it probably does, and that's why we need testing. Um, yeah, so that's a couple of, you think you're just going to design a thing, and then the whole thing spins kind of out of control. One thing I really like about the open source philosophy, when you're not talking about the uh, sharing of knowledge and alternative economies and the philosophy of the whole thing, is it also impacts your design approach. It's like you design things in such a way that they actually are easier to adapt or to work with for other people. But it's not just you design a thing and then you decide which way you go. It's actually you design a thing to go that specific direction. And I think I see you again, so I'm probably have just about reached the limit of my presentation.
We're coming up on the end.
Yeah,
But,
thank you so much. Yeah, Marteen, it's so cool to see like how this all comes together. Because when we talked about the eDNA sampler in Indonesia this year, because we were very lucky to hang out in Indonesia this year, I will admit that I didn't fully understand how it all came together, but getting to see this process really clarified a lot.
Oh, thank you. Thank you.
So thank you so much for joining us today and giving us a little insight on how you've been making this all come together in your project.
Sure. My pleasure. This was lovely. Looking forward to the second half.
All right, we'll
Us
talk
too.
soon.
Bye.
Yeah, talk soon.